Next section, the subspace topology. So let's first see the definition. Let x comma tau be a topological space and let y be a subset of x. Then the following collection is a topology on y. What are the elements in this collection? They are the intersection of all the open sets in X with Y. That means U intersection Y, where U is open in X, or in other words, U is coming from the topology tau on X. Note one thing, that at least these intersections are all subsets of Y. So it makes sense to say that they form a topology on Y, because a topology on a set is basically a collection of subsets of that set. But of course, just simply saying that this is a topology on Y does not automatically make it a topology. We have to verify it. But anyway, we will do so. So this topology is called the subspace topology. On Y you can write, but that's obvious. And in this case, we say that this space y comma tau y is a subspace of x comma tau of the original space. Or more simply, we also say like this, that just y is a subspace of x. Now the job we have is, we have to show that this collection really is a topology on y. So the first thing we note is, of course, this. It's clear that tau y is a collection of subsets of y, the thing that I said just now. And then we note this thing. We already know that the topology tau on X contains these two elements. It may have other elements, but these two in particular are always there, the empty set and X itself. So by the definition of the collection tau y, the intersections of these sets with Y will belong to this collection, that is the empty set intersection Y, which is the empty set, and X intersection Y, which is Y. So that way the empty set and Y are both inside the collection tau Y. This is one of the conditions for tau Y to be a topology. Next, of course, we have to show that the union of any subcollection of tau y is again an element in tau y, and the intersection of any finite subcollection of tau y is again an element in tau y. And next we do just that, we consider a subcollection of tau y, this V alpha, and we make it an indexed family or indexed subcollection, indexed by some set capital I. And you already know what this means. It just means that for each level alpha in I, V alpha is an element in tau y. Alright. So what does that mean? It means that each V alpha is going to look like this, some U intersection Y, and that's why we have this next thing. Then for each level alpha in I, there exists a U alpha in tau, such that V alpha is equal to U alpha intersection Y. Now what is it that we have to show here? We have to prove that the union of all these V alphas is again an element in tau Y. So we give a name to this union. Let the union of all these V alphas, as alpha varies over I, be V, be called capital V. Now simultaneously we note one more thing, that because all these U alphas are coming from tau, and tau is already a topology, so the union of all these U alphas would also be an element in tau. And now we look at V again. So in place of V alpha, you write U alpha intersection Y. And we are looking at the union of such intersections. But that is equal to this intersection of Y and the union of all the U alphas by one of the general De Morgan's laws. And now you use this fact, because this set after all is in tau. So what you are looking at here is something like this, a set in tau intersection Y. So by the definition of the collection tau Y, this is in tau y, that is V is in tau y. So we have proved that the union of any subcollection of tau y, union of any subcollection means union of the elements in any subcollection of tau y is in tau y. So that leaves us with only one more thing to prove, that the intersection of any finite subcollection of elements in tau y is again in tau y. Now instead of straight away seeing the general case, let us first take two sets in tau y, V1 and V2. As before, as was the case with the V alphas, here also there will exist two sets U1 and U2 in tau such that V1 is U1 intersection y and V2 is U2 intersection y. That comes from the definition of tau y. Now here also you note one more thing about U1 and U2. What did we note in the previous part? That the union of all the U alphas is in tau. In this case, the intersection of U1 and U2 is in tau. That is because tau is a topology and these are two open sets. That number 2 is a finite number. So the intersection is again in tau. And now we consider the intersection of V1 and V2, which of course is this, and because the only operation available here is intersection, there is no union or anything else. So this is just, you can see it very easily that it's just the intersection of all the three sets here, U1, U2 and Y. And there you can separately consider U1 and U2, their intersection, which belongs to tau, and that is why this set has precisely this form. So it will belong to tau y, and that's how V1 intersection V2 belongs to tau y. So we have proved that the intersection of any two elements in tau y is again an element in tau y. Using this fact and induction, which is a very simple thing, you can then prove that for any finite number of elements in tau y, their intersection is also in tau y. And that is why now we can finally say that yes, tau y really is a topology on y, and this is called the subspace topology on y. It is the subspace topology that has been inherited from the original topology tau, which is a topology on x. Next we have lemma 16.1. Let x comma tau be a topological space, and this time the topology tau is given by a basis. Let B be a basis for the topology tau, and let y be a subset of x. Because y is a subset of x and we already have a topology on x, so there will be the subspace topology tau y on y. So that is already there on y. Now the following collection, this collection will be a basis for that subspace topology tau y. What are the things in this collection? These are the intersections of all the basis elements from B with y. So it is somewhat like tau y itself. The only difference is that in tau y, we were considering intersections of y with the open sets coming from tau, but here more specifically we are only considering basis elements. So let us now prove this. So the first thing we note in the proof is this: since the basis B is itself a subset of the topology tau, so this collection By is a subset of the subspace topology tau y. Why? Oh, and by the way, where are we getting this from? You recall that in a topology, if there is a basis, then the basis elements in particular are also open sets. That is why this basis is a subset of tau. What does that mean? It means that if you take a B from B, here, if you are choosing a basis element B from the given basis B, then that capital B is also in tau. So by the definition of the subspace topology tau y, this intersection is in tau y. That is how any element in By is also in tau y. So By is a subcollection of tau y. Actually we need this before we can go for verifying the other conditions. Other conditions means there is only one more condition. For By to be a basis, you need to make sure that the elements in By are at least open in tau y, or in other words open in the space y. So we have verified that, and now we go for the main part. Next we take any point y in y and any open set V in the subspace topology tau y, so that V contains that point y, and we have to now show that there exists an element in this collection By, which of course looks like this for some B, that will contain the point y and will itself be contained inside V. If we can manage to show this, then this By will qualify to be a basis for not just a topology on y, but actually this topology, the subspace topology. Now next we concentrate on the fact that V is coming from tau y. So there exists a u in tau such that V is equal to u intersection y, because that's what tau y is. It has elements which look like this. Now because y belongs to V, so the point y belongs to u intersection y, and as a result y belongs to u. Okay, but what is u? U is coming from the topology tau, and B is a basis for tau, and the point y is inside u. So by the definition of a topology generated by a basis, there will be a basis element B in this collection B that will contain that point and will itself be contained in the open set U. Okay, next. So next you get this, but then y belongs to B intersection y, and B intersection y is a subset of U intersection y, which is V. How are we getting this? Well, the point y was already inside the subspace y, and now you found that y is also in B. So obviously y is in their intersection, and because B is a subset of U, so B intersection y is a subset of U intersection y, and U intersection y is nothing but V. So are you not getting what you wanted to get? What is it that you wanted to show? You wanted to show that for this setup, that a set V coming from tau y, an open set in the subspace which contains a point y, a given point, you wanted to find an element in this collection By which would contain that point and which would itself be contained in V, and that element is this B intersection y. It contains that point y and is itself contained in V, and it is actually a set in By. Why? Because of the form that it has, and because of the fact that B itself is coming from B. So by the definition of By, this is what you have, and that is why this collection By is a basis for the subspace topology, and the proof ends here. Next we have a language which will allow us to state things more simply. Suppose x comma tau is a topological space and y is a subset of x, same setup. Now suppose z is a subset of y. We will say that z is open in y if z is an element in the subspace topology on y, and similarly if z belongs to the original topology, then we would just say that z is open in x. Actually, even before writing it down formally, we were already using this terminology, that something is open in x. It means that it belongs to the topology that we have on x, or say on y, then it is open in y. Now using this term, we are next going to see one small result, and that result is lemma 16.2. Let y be a subspace of x. It's a little confusing to just simply say let y be a subspace of x. If you see this statement just somewhere, you may be confused because y may be a subspace of x as a vector space. But in the context of topological spaces, because we are discussing topology, so it makes sense. if U is open in Y, this means that U is a subset. This means two things, okay. First of all, U is a subset of Y, and the second thing is that U is open as a subset of the topological space Y. What is the topology on Y? The subspace topology tau Y. Although we do not really see tau here, we have to name those things, but that's the meaning. And if Y is open in X, that means Y is already a subset of X. Y being open in X means Y belongs to the topology that we have on X. Then U has to be open in X. Let me read it once more. If U is open in Y and Y is open in X, then U is open in X. So let's now see the proof. So this is the proof, pretty easy, and it's made short by naming these things properly. Let tau be the topology on X. Here there is no mention of topology, but we are giving it a name. Now, the condition that U is open in Y precisely means this, that U is an element in the subspace topology that Y has, which it inherits from tau, the topology on X. And because of this, and because of how we know tau Y is by its definition, there exists a V in tau such that U is equal to V intersection Y. Do not be alarmed by the role reversal here. You have been seeing V on that side and U on this side, but these are just variable names given to sets. Okay. If you want, no, you cannot of course write V here because it's already given that U is open in tau Y. Okay, so that's not a very big thing. So U is equal to V intersection Y. Now what do we know about V and Y? We already have said that V belongs to tau, and it's also given that Y is open in X. That means Y also belongs to tau, and because tau is a topology, their intersection is again in tau, which is nothing but U. And the fact that U is inside tau as an element is just expressed in words like this, that U is open in X. So there the proof ends.